Hello, everyone. Welcome. Happy Thanksgiving. I hope you're having a good break with you and your family and your friends. Thanks for tuning in here and doing your chemistry over your break. And we're just going to jump right in. I'm going to share my screen. And I realized at the end of the last lecture that I forgot to go over the exam. So let's just do a quick review of the exam before we get started on the material for today. So this is the statistics from exam 3. You can see the sort of range of scores here. I was very happy with these results. Let me just go over the questions quickly and provide you a little bit of background for the questions in cases where a lot were missed, and then we'll go ahead and start on today's material. So first question, energy that is associated with the position or composition of an object is called potential energy. Great job on that. The definition of energy is the capacity to do work. Great job on that. Which of the following signs on Q and W represent a system? So right when you see this, it's probably helpful to start making a little diagram for yourself. So you have a system, right? There's doing work on the surroundings, right? So if it's doing work on the surroundings, work is going out, right? So you know that work is going out carries a negative sign, right? And at the same time, it's gaining heat from the surroundings. So Q is coming in, so Q is positive, right? So that's the way you want to think about this problem. And so you can see the right answer here was this one. Q is equal to positive and W is negative. This problem, calculate the work when a cylinder equipped with a piston changes volume against an external pressure. So here, you just want to use the equation W is equal to minus P delta V to calculate the work. That's going to give you the work in liter atmospheres. And so then you just use this conversion factor right here to convert from liter atmospheres to joules, okay? An endothermic reaction, all right? So again, here it might be helpful to think again about the system and the surroundings. If it's endothermic, right, you know that energy or heat is going in, right? And so if it's going in, you know that that's going to be a positive, right? It's like a deposit to your banking account. So the right answer is this one. A positive delta H absorbs heat from the surroundings and feels cold to the touch. Again, remember, if you touch this, you're part of the surroundings. And so your finger is going to feel cold as energy is sucked out of your finger by the reaction. All right. This question, you got to find the heat associated with the combustion of 150 grams of octane, right? So you want to go from 150 grams of octane, convert that to moles of octane, right? And then once you have moles of octane, you're going to use the stoichiometry of the chemical equation, right? And so you know that you get 11,018 joules negative per 1 mole. Sorry, not per 1 mole, per 2 moles, right? And that's because of that 2 right here, right? And so once you do that, you'll get minus 7228 kilojoules. Again, nice job. Most of you got that. Then here, you have a reaction of HF, right? And the question is, how much must react to produce 960 kilojoules of energy? So again, this is the stoichiometry of thermochemical equations. So what you want to do is you want to start with 690 kilojoules. And then you're going to use the relationship between moles of HF and kilojoules here, right, to convert to moles of HF. So you have minus 184 kilojoules per 4 moles of HF, right? And that 4 there is the critical part, right? So that's going to give you kilojoules. And you want to produce 690 kilojoules actually, so that's negative, right? So that's going to give you moles of HF. And then you can go to grams of HF from there, right? And that's going to give you this number which is the correct answer. This one, you have two aqueous solutions that are mixed at room temperature and then mixed in the coffee cup calorimeter. A reaction occurs and causes the temperature of the resultant solution to fall. So again, it's kind of helpful perhaps to draw yourself a diagram here. You have the reaction happening here, which is the system, right? And you're told that the temperature falls, right? So if the temperature falls, that means energy is going into the reaction, right? So if you look through here, it's asking for a true statement, right? So this one was a little bit tricky. Let's just go through each of the wrong answers here. This type of experiment will provide data to calculate delta E. No, because only a bomb calorimeter provides delta E, right? This provides delta H. The products have a lower potential energy than the reactants. No, because this reaction is endothermic. So the products actually have a higher potential energy. Energy is leaving the system during the reaction. No, energy is coming into the system, right? Because it's an endothermic reaction. The reaction is endothermic. Again, that's incorrect. So the correct answer was none of the above. Now, as you can see from the statistics here, so few people got this, that this was the question that I decided to make an extra credit question. So if you missed this question, you didn't lose any points. If you happen to have got it right, then good job, and you got a couple points of extra credit for this. All right, let's go on. For this problem, you got to use the standard enthalpies given to find delta H for this reaction. So you got to manipulate these reactions so that you can add them together to get to this reaction, right? And then if you do that, then you can add together the delta H's. And the right answer was this first one here, minus 1583 kilojoules. In this reaction, you had to use the enthalpies of formation to get delta H for the reaction, right? And this is the reaction that you're looking for to get delta H. The enthalpies of formation are given here. So it's the enthalpies of formation of the products minus the enthalpies of formation of the reactants. And if you do that, you get negative 62 kilojoules. Again, nice job on that one. The number of wave cycles that pass through a stationary point in a given period of time is called the frequency. Most of you got that. Very good. The distance between adjacent wave crests is called wavelength. Most of you got that. Which of the following visible colors of light has the longest wavelength? Red. So red is the long wavelength end of the spectrum. Violet is the short wavelength end. Okay, so a few of you got that one wrong. When waves of equal magnitude, equal amplitude from two sources are out of phase, when they interact out of phase, right? Out of phase is when they interact like that. And that results in destructive interference. When a wave encounters an obstacle or a slit that's comparable in size to its wavelength and bends around it, this is diffraction, okay? Then here we want to calculate the wavelength of blue light emitted by a mercury lamp with a frequency of 6.32 times 10 to the 14 hertz. So we know the relationship between wavelength and frequency is this, right? Nu is equal to C over lambda. So here you just have to solve that. Lambda is equal to C over nu, and you plug that in and you get 475 nanometers. For this problem, you want to figure out the number of photons contained in the flash of green light that contains a certain amount of energy. So the first thing to do is to use the equation E is equal to HC over lambda. And that's going to give you the energy of one photon of this wavelength, right? The wavelength is 525 nanometers. And then whatever you get for that, you take 189 kilojoules, which is the total amount of energy, and you divide by the energy for each photon, and that'll give you the number of photons. So it's 4.99 times 10 to the 23. Calculate the wavelength of an electron moving at a certain speed. So that's the wave nature of matter, right? Lambda is equal to H over mv, right? So you use that equation, plug in Planck's constant, the mass of the electron, which is given, and the velocity. you do have to change that to kilograms, and that'll give you the wavelength. For n equal 3, what are the possible values of L? Well, you can go all the way up to n minus 1. So it's 0, 1, and 2. What is the value of L? What value of L is represented by a d orbital? Well, d means L equal 2, right? So that's 2. Choose the valence orbital diagram that represents a ground state of nickel. And don't have a picture for this one, but most of you got that, so I think we're in good shape for that one. Which of the following statements is true? Now, this was a question that had more than one possible answer. And so for this question, I just threw it out. And what that means is that if you got this question right, you got your 2 points. If you got this question wrong, you got your 2 points because the question was flawed. So we'll skip over that one. Next one, give the ground state electron configuration for arsenic. Again, most of you got that right. It's this one. The main thing there was just to be able to read from the periodic table what the electron configuration was. How many valence electrons do the halogens possess? Well, here, the important thing was to realize what the halogens are. The halogens are these elements right here, right? And so that's group 7, and they have 7 valence electrons, okay? Give the ground state electron configuration for O2 minus. And so that was 1s2, 2s2, 2p6. Most of you got that, so nice job. Choose the correct ground state electron configuration for titanium 2 plus. So titanium is right here, right? So its neutral electron configuration is 4s0, 3d2. But remember, when you form the ion, you always lose the s electrons first. So it's 4s0, 3d2. Choose the statement that is true. Core electrons effectively shield outer electrons from nuclear charge. And most of you got that. Nice work. What period 3 element has the following ionization energies? Well, what you can see here is that the ionization energies go up pretty regularly, 1 to 1,000, 2,000, 3,000, 4,000, 7,000, 8,000, and then you have a big jump to 27,000. So remember, the jump occurs between the last valence electron and the first core electron. So what this is telling you is that you have all of these electrons here are all valence electrons. So another way you can interpret this, that would be what period 3 element has 6 valence electrons. So you go to period 3, count over 1, 2, 3, 4, 5, 6, right? And you see that it's sulfur. Okay. Place the following in order of increasing atomic radius. So notice as you trace the line from fluorine to nitrogen, you go to the left, that's bigger. And then if you go down to arsenic, you go down, and that's also bigger. So the answer is this one. Place the following in the order of decreasing metallic character. All right, if we start with potassium, the most metallic, we go to the right, that gets less metallic to arsenic. And then as we go up, it gets less metallic to phosphorus. Okay, the temperature rises from 25 to 29 degrees in a bomb calorimeter when you have a certain amount of sucrose, and you got to calculate delta E. All right, so 3 steps in this. First, you calculate, sorry, let me get rid of this periodic table. First, you calculate Q calorimeter, right, which is equal to C calorimeter times delta T. All right, and you're given C right here. Okay, and you can calculate delta T from that. And then you want to do Q reaction is equal to minus Q calorimeter, right? So you just change the sign. And then lastly, delta E is equal to Q reaction divided by the number of moles of sucrose, which you can get from the mass of sucrose and the molar mass of sucrose. All right, this, a good number of you got this, about half you, but this was a hard problem, all right, because it was a little bit tricky. this is coffee cup calorimetry. So you're going to follow kind of the similar steps as you did for bomb calorimetry, except for here, you're going to do Q calorimeter is equal to MC delta T, where M is the mass of the solution, right? And the solution mass is 100 milliliters plus 100 milliliters is 200 milliliters times the density of 1 gram. So that's going to be 200 grams, right? And then you can use the heat capacity of water for C, right? And then delta T you get from this. Now, the next part of it is you're going to say, okay, Q reaction is equal to minus Q calorimeter, right? So you just change the sign. And then it's the last part that's a little tricky because delta H is equal to Q reaction divided by the number of moles that reacted, right? But in this case, you have 100 mils of 0.1 molar AgNO3. So that corresponds to 0.010 moles of AgNO3. And then you have 100 mils of 0.2 molar NaCl. So that corresponds to 0.020 moles of NaCl. So notice the reaction stoichiometry is 1-to-1, right? So you have 0.1 moles of this and 0.2 moles of that. So this is the limiting reactant. So how many moles actually react? 0.01. So when you do this last step, the number of moles of reactant is 0.010 moles. Okay, and then that gives you minus 59 kilojoules. All right, determine the wavelength of light emitted when a hydrogen atom makes a transition from n equals 6 to n equals 5. So here what you want to do is you want to figure out what delta E is. Delta E is equal to E5 minus E6, right? And then from there, you want to set that equal to HC over lambda and find the wavelength. And you get this answer right here. Okay. All right, that's the exam. If you have any individual questions, feel free to drop me an email and I can meet you over Zoom and we can go over your exam. But otherwise, again, very good job. Thank you for your hard work on this exam. It wasn't an easy exam, but I'm very pleased with the results. Again, I wish there was no one down here in this range. And if you'd like to speak with me in terms of strategies to help you do better, I'm always happy and available to do that. But essentially, there's nothing you can really do to improve your score on this exam, but you can improve your score on future exams. And of course, we still have one more exam left in this class and the final exam. So there's a lot of room even yet for improvement. All right, so let's stop that. And we'll jump into chapter 11, okay? So let me just get a new piece of paper. Okay. So if you remember last time, we introduced Vesper's theory, valence shell electron pair repulsion. And that theory is going to help us to predict the geometry of a molecule from its Lewis structure, right? And last time we talked about the 5 basic shapes that occur when you have all the electron pairs around a central atom being bonding electrons. But now we're going to consider what happens when some of those electrons around a central atom are lone pairs. So, for example, if we look at the Lewis structure for ammonia, it looks like that, right? And so you have 1, 2, 3, 4 electron groups, but one of them is a lone pair. So how do we deal with that when predicting the geometry of the molecule? Well, I want to distinguish real quickly between the electron geometry and the molecular geometry. So the electron geometry is the geometry of the electron groups. And an electron group may be a bonding pair, right? So a chemical bond, it could be a double bond. It could be a triple bond, but it could also be a lone pair, okay? And so when we count electron groups, we want to count each bond as one, so that's 1, 2, 3, plus the lone pair as 1, so that's 4. So we have 4 electron groups. We can then go back to our table here and see that when you have 4 electron groups, right, the electron geometry is always going to be tetrahedral, okay? So the electrons themselves, the 4 electron groups, 1, 2, 3, 4, are going to assume this tetrahedral geometry. However, one of those electron groups is a lone pair. It's not really part of the bonding of the molecule, right? So that lone pair still exerts the force against these other bonding pairs. The resulting molecular geometry is like this. It's trigonal pyramidal. The angles between the 4 electron groups are 109.5. That's what we'd expect, right? If all the electron groups were the same. But when one of them is a lone pair, the lone pair actually occupies a little more of the angular space and exerts a little bit greater repulsion. So when we measure the bond angles in ammonia, it's not the ideal tetrahedral bond angle of 109.5, but rather it's squished down a little bit. So it turns out to be 107 degrees. If we draw the Lewis structure for water, looks like this. We see that water has, again, 4 electron groups, 1, 2, 3, and 4. Okay. 2 of those are lone pairs, but the electron groups, the 4 electron groups, still assume this electron geometry that is tetrahedral, right? Notice the tetrahedral arrangement of the 4 electron groups. Since 2 of those are lone pairs, though, the molecule itself is bent, right? So water is a bent molecule like this. Now, in terms of bond angle, again, the ideal tetrahedral bond angle is 109.5. But for water, because 2 of those are lone pairs, the lone pairs, again, exert a greater repulsion than the bonding groups. And so this is squished down, right? It's 104.5. The order of repulsions is always going to be lone pair. Lone pair is the strongest repulsion. That's greater than lone pair, bonding pair, which is greater than bonding pair, right? So the repulsion between these 2 lone pairs is the greatest. This is the least. And then the repulsions between a lone pair and a bonding pair are in between the 2, right? But that's why you can see that this one gets squished down, okay? We can see this effect of lone pairs on molecular geometry if we compare methane, ammonia, and water, right? And we measure the bond angles. We can see that when there's no lone pairs, we get the idealized bond angle of 109.5 degrees. For ammonia, which has 1 lone pair right here, we get the bond angle squished down a little bit to 107. And then for water with 2 lone pairs, it gets squished down even more to 104.5. All right. So what happens if we have 5 electron groups with 1 lone pair? Well, again, what would you expect for the electron geometry of this? 5 electron groups, right? The electron geometry is trigonal bipyramidal, right? Trigonal bipyramidal. So the trigonal bipyramidal geometry looks something like this, but now you have a choice as to where there are 2 options as to where the lone pair might go. So remember, in the trigonal bipyramidal geometry, you have two kinds of sites on that geometry. You have the axial sites, which are these, and then you have the equatorial sites, which are the ones along the equator. Okay. If the lone pair were to go here, it would experience 3 90-degree lone pair bonding pair repulsions. But if you put the lone pair on an equatorial position, it only experiences 2 90-degree lone pair bonding pair repulsions. So this turns out to be the more stable orientation. So when you have 5 electron groups and 1 lone pair, you get this geometry, which is called a seesaw geometry. Why? Because if you turn it this way, it kind of looks like a seesaw, right? Go back and forth. All right, what if you have 5 electron groups, 1, 2, 3, 4, 5, and 2 of those are lone pairs? Again, the electron geometry you get from counting the electron groups. So since there's 1, 2, 3, 4, 5, the electron geometry is again going to be trigonal bipyramidal, as you can see here. Where do the lone pairs go? Well, again, in order to minimize repulsions, they are going to go in the equatorial positions. That's where the lone pair, where all the electron-electron repulsions cause the minimum amount of repulsions. All right. So the molecular geometry ends up being T-shaped. All right. You could also have 5 electron groups with 3 lone pairs, like in xenon difluoride here, right? 5 electron groups, 1, sorry, let me go back to that. 5 electron groups, 1, 2, 3, 4, 5, right? So again, trigonal bipyramidal electron geometry, the 5 electron groups, 1, 2, 3, 4, 5. Where are the lone pairs going to go? Again, in this case, they minimize their repulsions with everything else at the equatorial positions. Okay, so the molecule ends up being linear. Here you have 1, 2, 3, 4, 5, 6 electron groups. So this is our first candidate with 6 electron groups. And 6 electron groups, we know that the electron geometry is going to be octahedral. Remember octahedral, 1, 2, 3, 4, 5, 6, right? Where does that electron pair go? Well, it doesn't matter in this case because all sites are equivalent, right? So no matter where you put it, you're going to get the same geometry, and that's this square pyramidal geometry. Here you have xenon tetrafluoride, which has, again, 6 electron groups. So the electron geometry is going to, again, be octahedral. The 2 lone pairs are going to go opposite of each other to minimize their repulsions. And so the molecule is going to end up being square planar. Okay, so how do we predict molecular geometries for any molecule? We just look at the molecule, count the number of electron groups, see how many of those are lone pairs, and then figure out the geometry from there. This table in your book summarizes all the different possibilities, right? The ones that I've put in boxes here are the ones that have no lone pairs, which are what I call the basic geometries, right? Trigonal, planar, tetrahedral, and so on, right? And then you see what happens when you have some lone pairs. So visit this table and make sure you understand how to predict both the electron geometry and the molecular geometry for a molecule from its Lewis structure, okay? All right, let's pretend we're in class and I'm going to ask you a question and you go ahead and think about it and see if you can come up with the right answer. I suggest you just pause the video right now for a second and go ahead and try to come up with an answer to this question and then test yourself to see if you're right. So pause now. Okay, hopefully you got the right answer, and the right answer was C, trigonal pyramidal. Why? You look at the central atom, you count the number of electron groups, 1, 2, 3, 4 electron groups, 1 lone pair, right? So you can go back to this table and see 4 electron groups are here, 4 electron groups, 3 bonding groups, 1 lone pair. The electron geometry is tetrahedral, right? But the molecule is trigonal pyramidal, okay? All right. This little table, which you can find in your ebook as well, just shows you how you can draw some of these structures on paper, right? So the ones that you can get all on one plane are pretty straightforward. You can draw them with straight lines. But then the ones that you can't, that are three-dimensional, you want to use these little dashes and wedges to help you draw them. So a dash means it's going into the paper, and a wedge means it's coming out of the paper, right? So in this case, you have this bond going into the paper and this bond going out. Here is the seesaw shape. So you see these three atoms are in the plane of the paper, one going in and one coming out. Anyway, you can review this on your own to see how you can represent these on paper when you're working out problems. Okay, what if you have multiple interior atoms instead of just one? How do you figure out the geometry of a molecule like that? Well, you can just figure out the geometry about each individual internal molecule based on the number of electron groups and lone pair on that central atom. So here is an amino acid, glycine. Amino acids are the building blocks of proteins. So this is a larger molecule than what we've seen so far. And what you can do is you can just go through and figure out what the geometry is about each atom, right? So here we have a nitrogen atom with 4 electron groups, 1 lone pair. So we know that's going to be trigonal pyramidal. Here we have a carbon atom with 4 electron groups, no lone pair. So that's going to be tetrahedral. Here we have a carbon atom with 3 electron groups. Remember, a double bond counts just as a single electron group. So that's going to be trigonal planar. Here we have an oxygen atom with 4 electron groups and 2 lone pairs. So that's going to be bent, right? So we can summarize it here and we can put all this together and we can get a shape for the entire molecule by focusing on each individual interior atom at a time. Okay, so one of the properties of molecules that is severely impacted by the shape is the polarity of a molecule. So remember we talked about polar bonds earlier. A polar bond is one where you have separation of charge, right? So that you have a positive end and a negative end. For a diatomic molecule, if you just have 2 atoms in a molecule, right? If you have a polar bond, you have a polar molecule. However, for molecules that contain more than 2 atoms, we have to consider the geometry of the molecule in order to predict polarity. So remember, we talked about HCl. It has a polar bond, right? Partial positive end, partial negative end. Again, in a molecule that just has 2 atoms, if the bond is polar, the molecule will be polar. However, here's carbon dioxide. Carbon dioxide, we know from earlier and from the structure that it has a linear geometry, right? Now, carbon and oxygen have different electronegativities. So oxygen is more electronegative than carbon, so we know that these bonds are polar. But notice that the bonds point in opposite directions, right? And as a result, the polar bonds are going to cancel each other out because you have a dipole pointing this way and a dipole pointing that way. And by vector addition, if you add 2 vectors that point exactly opposite directions and are exactly the same length, they're going to cancel each other out. So carbon dioxide is a non-polar molecule. On the other hand, consider water. Water also has 2 polar bonds, but because of the electron pair, the lone pairs on the oxygen, its molecular geometry is bent, right? And so now you have a polar bond this way and a polar bond that way, and these don't cancel each other out. So you get a net dipole moment, and water is very polar. This influences the properties tremendously. Carbon dioxide is a gas at room temperature because the molecules are not attracted to each other by these dipole moments, whereas water is a liquid at room temperature because the water molecules are attracted to each other by these dipole moments. How do you determine if a molecule is polar? Well, you got to add together the polar bonds as if they were vectors, right? So go through this little diagram in your book that kind of shows you how to do that and how to add together vectors to determine if a molecule is polar. But at the end of the day, what you're looking for is symmetry, right? Molecules that are very symmetric, like carbon dioxide, the polar bonds could cancel out. molecules that are not symmetrical like water, the polar bonds won't cancel out. So let's do a couple of examples. Let's decide whether each of the following are polar. So here we have this molecule. We look at the Lewis structure and we can determine the molecular geometry. It has 1, 2, 3 electron groups, right? So we know that the molecule is going to be bent. So the shape of the molecule is going to be something like that. All right, these bonds are polar, right? Because the nitrogen, the oxygen, the chlorine all have different electronegativities, right? So we have a polar bond pointing in that direction and a polar bond pointing in that direction, right? If we add those two vectors up, we see that that results in a net dipole moment. So this molecule would be polar. One way you can kind of think about this is you can think of each polar bond as kind of a dog on a leash. So imagine this nitrogen atom had 2 dogs on leashes and one's pulling in this direction, one's pulling in that direction. Do the pulls cancel each other out? Well, no, in this case, they don't, okay? But now let's look at SO3 over here. 1, 2, 3 electron groups, right? So the molecular geometry is trigonoplanar. So it looks like this. Sulfur and oxygen have different electronegativities, so the bonds are all polar. But you can see that this is much more symmetrical than this, right? And so again, imagine, sort of 3 dogs on leashes all pulling on this sulfur atom. Since they're pulling in these at 120-degree angles from one another, they're going to cancel out, right? And SO3 is going to be nonpolar. Okay, the polarity of molecules again affects many of their properties. We already saw how water is a liquid at room temperature instead of a gas because it's polar. Polar and non-polar substances tend to separate from one another. Like here, oil is very non-polar, water is very polar. The water molecule, the polarity of the water molecules cause them to stick together, and they basically push the oil molecules out, right? So you can kind of think about this as a mixture of magnetic marbles and non-magnetic marbles. The water is like the magnetic marble, the water molecules are like the magnetic marbles, and the oil molecules are like the non-magnetic ones. And you can see that the magnetic ones will clump together, right? So the water molecules clump together here. What happens is that the opposite poles of the molecule attract one another, right? The plus and the minus attract one another, just like the opposite ends of a magnet attract one another. Okay, so we've gone through Vesper. This is the end of the Lewis model of chemical bonding. We can see how powerful the Lewis model is, and we're going to be obviously using it, right, to predict a lot of things about molecules, including their shape, right, and their ability to have polarity. Okay, so next we will look at the second of our 3 bonding theories. So remember that our 3 bonding theories are going to be the Lewis model, which we've just covered, and the Lewis model, the chemical bond is a shared electron pair. Our next model is going to be the valence bond model, or valence bond theory. Here, a chemical bond is the overlap between 2 half-filled atomic orbitals. And then our last theory that we're going to look at on Monday in class is going to be molecular orbital theory. And here, a chemical bond is going to be measured by something called bond order. So we'll cover that in class on Monday. For right now, we're going to look at valence bond theory, in which a chemical bond is the overlap between two half-filled atomic orbitals. Sorry about that. Okay, so let's jump into it. We can actually calculate the energy of an electron. Well, we already know how to calculate the energy of an electron in an s orbital in a hydrogen atom, right? We solve the Schrodinger equation for that atom, and we get the different energy states. Now, we can also calculate what happens to the energy of an electron in that 1s orbital of the hydrogen atom when one hydrogen atom approaches another hydrogen atom. So this is a plot of the energy that happens as a result of that interaction. So when they're far apart, we're just going to say, there's no interaction energy between them. But as they come closer and closer together, we see that the energy of the electron in those orbitals drops down, lower and lower and lower. It gets to a minimum right here, and then it goes back up because now the nuclei start to repel one another, all right? And it's this lowering of energy that is the chemical bond, and that results in the bonding of the two hydrogen atoms. Using valence bond theory, we can calculate not only that a chemical bond will happen because the energy drops down when they get close to each other, but we can calculate the strength of the bond, which is going to be the difference between here and here. And we can actually calculate the length of the bond, which will be the distance from here to here. In other words, where that minimum in the energy curve happens. So what we find is that this kind of curve occurs whenever we bring two half-filled orbitals in close proximity to one another. If these orbitals were filled instead of half-filled, we'd get a curve that would look like this. If we plot the energy of interaction for two filled orbitals, we get a curve that looks like this. The energy just goes up and up and up, right? And that means that the two atoms are not going to be attracted to one another, and that a bond will not form between those two filled orbitals. So what does that mean? That means we can look at the electron configuration of atoms. We can look to see if they have half-filled orbitals. If they have half-filled orbitals, then we can say, aha, chemical bond is going to form between those half-filled orbitals. So for example, here's the electron configuration for sulfur. It's 3s2, 3p4. From the orbital diagram, we can see that it has two half-filled orbitals. So those half-filled orbitals can form chemical bonds with hydrogen atoms. So for example, if we apply valence bond theory to H2S, we can say, aha, here's the sulfur atom. It has some filled orbitals. It has an s orbital here, which I'm not going to draw because it's filled. It has a 3p orbital that I'm not going to draw because it's filled. It's not going to be involved in bonding. But I am going to draw these two half-filled 3p orbitals. So here's one of them, and here's the other one, right? And each of those orbitals has one electron in it, like that, right? So let's get a different color. Easier to see on the screen. We'll make those red. It looks kind of like that. Then you have the hydrogen atoms, which also have half-filled orbitals, s orbitals. So the hydrogen atom has an s orbital, and the other hydrogen atom has an s orbital. And it's this overlap between half-filled orbitals that we call a chemical bond, all right? Because that's going to lower the energy of the electrons in those orbitals, right? So here's the total picture, drawn a little bit more clearly. Here's the hydrogen atoms, each with a half-filled orbital. Here's the p orbitals on the sulfur. There's going to be an overlap there and an overlap there, and those are going to be the chemical bonds. This image is also showing the filled p orbital and the filled s orbital, which are not involved in bonding. But in general, from now on, we're not going to draw those filled orbitals because they're not going to be important in bonding. Since the angle between these half-filled orbitals is 90 degrees, right? Because they're p orbitals, and we know p orbitals are orthogonal to one another, we would predict that the H2S molecule has a bond angle of 90 degrees. We go out into nature, we measure the bond angle of H2S, and it's a little bit more than 90 degrees, about 92 degrees, but pretty good agreement with experiment, right? So this is the way valence bond theory works. The overlap of half-filled orbitals creates chemical bonds, and the geometry of the molecule is, of course, determined by the geometry of the overlapping orbitals, right? In this case, because the overlapping orbitals have a bond angle of 90 degrees, the molecule has a bond angle of 90 degrees. Okay, again, let's pretend we're in class. Here's a question for you that you can answer on your clicker. Of course, you don't have any clicker here now, so just pause the video and try to answer this question. All right, the correct answer to the question is 1, right? According to valence bond theory, what is the maximum number of bonds that can form with an atom that has an outer electron configuration of 2s2, 2p5? Well, if we draw the orbital diagram, 2s2, 2p5 would be 1, 2, 3, 4, 5. So how many half-filled orbitals do you have? Just 1. So how many bonds can you form? Just 1. Okay. All right. Now, the next step in valence bond theory is this process called hybridization. Hybridization means that the atomic orbitals of an atom can turn out to be a little bit different when that atom forms a molecule. And we can approximate what those orbitals look like by a mathematical process called hybridization. And the reason we need hybridization is because without hybridization, the theory ends up not being able to predict a lot of what we see. So for example, if we were to try to apply valence bond theory without hybridization to methane, CH4, or the compound, that forms between carbon and hydrogen, we'd say, oh, okay, carbon has 4 valence electrons, right? So it has an electron configuration of sp2, 2 s electrons, and then the p electrons also 2, because 4 total, right? So according to valence bond theory, it seems that carbon would only be able to form 2 bonds, kind of like sulfur did, right? And those bonds would be through p electrons that have a 90-degree bond angle. So if we apply the simple idea using just the normal atomic orbitals to carbon and hydrogen, we predict that we would get a molecule of CH2 with a 90-degree bond angle. But that's not what we get. As we know already, carbon and hydrogen form methane, CH4, and it has a tetrahedral shape and a 109.5-degree bond angle. So how does this happen? Well, it happens through this process called hybridization. So what is hybridization? Hybridization is a mixing of atomic orbitals to form what are called hybrid atomic orbitals. And the rules for hybridization are that however number of orbitals you mix is equal to the number of orbitals, hybrid orbitals that you get out. So in this case, we're mixing an S and 3 Ps. We put 4 in, we get 4 out, okay? These 4 hybrid orbitals, we label them sp3 hybrids. Why sp3? Because they're a combination of 1s and 3p. So this is a mathematical mixing of orbitals to form these hybrid orbitals. Notice that in the case of the s and p orbitals, they have different energies. In the case of these hybrid orbitals now, they all have the same energy, all right? They're all degenerate. So when you put the 4 electrons that are in carbon into the hybrid orbitals, they occupy them singly with parallel spins. And now you can see that with hybridized carbon orbitals, you can form 1, 2, 3, 4 bonds. What do these orbitals look like? Well, we know what the s orbital looks like and the 3p orbitals look like. When we mix them mathematically, they end up looking like this, all right? These are the 4 new orbitals that come out. And if we put them all together in the same diagram, they look like this. And you see that they have this tetrahedral geometry. Now, why does hybridization happen? Well, it happens because hybrid orbitals are better at forming chemical bonds than the normal atomic orbitals. And that's because, as you can see here, they have kind of one big lobe and one small lobe. So a lot of the electron density is shifted over to one side compared to a p orbital where the electron density is sort of evenly divided between the two sides. What does that mean? That means that this big lobe can overlap more with the neighboring orbital. And that greater overlap allows for more energy lowering, right? And therefore better ability to form chemical bonds. So here's what CH4 looks like with the 4 hybrid orbitals overlapping with the 1s orbitals on the hydrogen. These are the sp3 orbitals right here, 1, 2, 3, 4, and these are the hydrogen orbitals. And these are the sp3 orbitals, and these are the hydrogen orbitals. We can also put lone pair electrons into hybridized orbitals. So for ammonia, it has 1 lone pair electron here in one of the hybrid orbitals, and then it's forming 3 bonds to hydrogens. Notice that there's a sort of correspondence between the Lewis model and the valence bond model. Here's the Lewis diagram for NH3 right here, right? And you can see that it has a lone pair. You can see the lone pair there in ammonia with the valence bond model, okay? So this is the Lewis model over here. This is the valence bond model over here. Notice in the Lewis model, a bond is a shared electron pair. Here, it's the overlap between half-filled orbitals. Those orbitals could be the standard orbitals, as we saw with H2S, but more often, they're going to be hybrid orbitals, like the ones you see here. Okay, and here. All right. Other hybridization combinations are also common. So we can combine 3 p orbitals and an s orbital to form sp3 hybrid orbitals, but we can also leave some of them out. So we can leave out this p orbital and just combine 2 p orbitals with an s. And then because we're combining 3, we only get 3 out. And those are called sp2 hybrid orbitals. And that leaves behind an unhybridized p orbital. This is what those orbitals look like. All right. They are trigonal planar in overall geometry. But again, notice the bigger lobe on one side and the smaller lobe at the other, which makes them more capable of forming chemical bonds. A molecule that has sp2 hybridization is formaldehyde. So if we have carbon, hydrogen, hydrogen, oxygen. Let's see. Sorry, let me get this on screen here. All right. So you can have this molecule. So there's 2 electron pairs here. This carbon atom has this sp2 hybridization. So I can draw it like this. This sp2 hybrid is going into the board. This one's coming out of the board. And then I have, let me go back to this. These are the 3 sp2 hybrid orbitals, 1, 2, 3. And then we have this unhybridized p orbital, which I'm going to draw right here. Okay. And the reason that's important is because carbon's 4 electrons are going to occupy sp2 and p. The 4 electrons will be 1, 2, 3, 4. They're going to occupy it like that. So in other words, each of these orbitals has 1 electron. So notice that carbon can again form 1, 2, 3, 4 bonds. 3 bonds with the hybrid orbitals and 1 bond with the unhybridized orbital. So the hydrogen atoms are I'm going to put over here. Hydrogen atoms have one s orbital, right? I'm going to start labeling these bonds as to, first of all, the type of bond they are, and secondly, the orbitals that are overlapping. So this type of bond is a sigma bond. I'll explain more what that means in a minute. The overlapping orbitals are hydrogen s orbital overlapping with a carbon sp2 orbital. All right, and this orbital is going to be exactly the same thing, right? I'm sorry, that bond. And then on this side is where we're going to bond with the oxygen. So oxygen, remember the electron configuration for oxygen, s, p, 6 valence electrons. So 1, 2, 3, 4, 5, 6. Oxygen has 2 half-filled p orbitals, which are available for bonding. I'm going to draw one like this and one like this. The s and the other p orbital are full. I'm not going to draw those. So this has an electron and this has an electron, right? So now you can have overlap here. That's going to be another sigma bond, which we're going to label as sigma carbon sp2 overlapping with oxygen p, because it's now a p orbital on the oxygen that's doing the overlapping. And then this new type of bond, which is side-by-side overlap between the p orbitals, okay? And that type of bond, we're going to call a pi bond. So that's going to be pi carbon p overlapping with oxygen p. And this is sort of our full valence bond picture of this molecule, all right? Here's the Lewis model. Here's the valence bond model. In the valence bond model, you see that all the bonds are overlap between half-filled orbitals, okay? The half-filled orbitals could be the standard p orbitals like they are here in oxygen, or they could be hybridized orbitals like they are in carbon. But carbon, even though we're using the hybridized orbitals here, we're also using the unhybridized p orbital to form that pi bond, all right? This just kind of shows another picture of it a little bit better. Here's the Lewis structure for this molecule, and here's the valence bond model for this molecule. All right, you see the 3 sp2 hybridized orbitals here forming 3 bonds, right? And then the p orbital overlapping with the p orbital here on the oxygen to form the pi bond. So what is this pi bonding? Pi bonding is always going to be sideways overlap between 2 p orbitals, right? So you're going to have a p orbital overlapping the p orbital, and they overlap in this area here and here to form a pi bond like that. A sigma bond is going to be face-to-face or end-to-end overlap between either a p and another p, or a hybrid orbital and another hybrid orbital. But the overlap's always going to be this way, end to end, instead of side by side. Okay, so this we call a sigma bond, this we call a pi bond. Sigma bonds and pi, this picture, this valence bond picture, gives us more insight into what a double bond is, right? So notice that this double bond here, what we drew in the Lewis model, makes it seem like both of those bonds are identical, where in fact they're not. One is a sigma bond, which is this kind of overlap. One is a pi bond, which is overlap above and below the plane. Now, why is that important? That's important because in a sigma bond, you get free rotation. So in other words, if I have this molecule, notice a single bond between these 2 carbon atoms, that's just a single sigma bond, and that can rotate. So that this molecule has free rotation. On the other hand, if I have a double bond, notice that the overlap is here and here. If this starts to rotate, it would break that double bond. So here you have restricted rotation. So again, if we just have a single bond, you have free rotation. So there's really no difference between these 2 molecules because this can rotate anyway. On the other hand, if I have a double bond, this is locked in place. And these 2 atoms got to stay on the side that they are. So these 2 molecules are essentially identical to one another. but these two molecules are isomers of one another. And you can see, for example, that these two bonds are polar, and since they're pointing in roughly opposite directions, they tend to cancel each other out. Whereas here, the two polar bonds are pointing in the same direction, they tend to reinforce each other. So this molecule ends up being much more polar than this one. So this molecule has different properties from that one for that reason. Okay, other possible hybridizations are sp. Here we mix one s and one p, and we get two sp hybrid orbitals, and we're left with two unhybridized p orbitals. When we mix these, it looks like this. We take a 1s and 1p, and we get our two hybrids. These are linear in overall geometry. So here's a molecule with sp hybridization. We have the two carbon atoms. They have sp hybridization. So they are going to form a sigma bond with a hydrogen atom, and then a sigma bond with the other carbon atom via those sp orbitals. But then notice that when we have sp hybridization, right, we have these leftover unhybridized p orbitals. All right, and those unhybridized p orbitals can also be involved in bonding. And so notice here in this molecule, we have the unhybridized p orbital here and here, and we form a pi bond, and then we form another pi bond with the other two unhybridized p orbitals. So this again gives us insight into the nature of a triple bond. What is a triple bond? A triple bond is one sigma bond and two pi bonds, one here above and below, and one here behind and in front of. Again, notice I've labeled each of these bonds using that same notation, right? Sigma, carbon sp, hydrogen s for these. This is sigma, carbon sp overlapping with carbon sp. And then here are my two pi bonds. Notice pi bonds are always between what? Side-to-side p orbitals. We can also get hybridization that involves the d orbitals. So I can get sp3d hybridization, which together have a trigonal bipyramidal geometry, and I get 5 of those. So for example, this molecule, ASF5, here's the Lewis structure, here's the valence bond model. The valence bond model is showing the 1, 2, 3, 4, 5 sp3d orbitals overlapping with p orbitals on the fluorine. In addition, I can have sp3d2 hybridization. This results in 6 hybrid orbitals. Remember, the number of orbitals you put in equals the number you put out. These assume a octahedral geometry. An example of a molecule with this hybridization is SF6. Here you see the sulfur with its 6 sp3d2 hybrid orbitals overlapping with fluorine orbitals, p orbitals. Okay, so let's have, again, another quick question here. Which of the following hybridization schemes allows for the formation of at least one pi bond? Pause the video here, answer the question, start it again when you finish. The correct answer here is B, right? You must have an unhybridized p orbital to form a pi bond, okay? Here the p orbitals are all used up. Here they're all used up as well. They're all used up in hybridization, so there's no unhybridized p orbitals left. When you have an sp2 hybridization, you have an unhybridized p orbital, and that is what can form a pi bond. All right, so how do we write these hybridization and bonding schemes? How do you decide what gets hybridized and what doesn't? So we're going to use a simple rule. And when you really do valence bond theory in detail, you would actually calculate the energies of each of the atoms and their electrons to determine what gets hybridized and what doesn't. What we're going to do is we're just going to say, okay, central atom or interior atom is always hybridized. Terminal atoms are never hybridized, right? So you saw this in some of the examples we just looked at. The sulfur here is hybridized. The terminal atoms are not hybridized, right? Saw that here as well. Central atom is hybridized. Terminal atom is just using its unhybridized p orbitals, right? Saw that here. Well, in that case, that doesn't really apply. The other one we saw it with was this molecule. Oxygen is terminal, so it's unhybridized, right? It's just using its unhybridized atomic orbitals. Carbon is central, so it is going to be hybridized. So that's what we're going to use, that rule of thumb. It works most of the time. It doesn't work all the time, but we're going to assume it works all the time. The next thing we got to decide is, well, what kind of hybridization are we going to have on that central atom? Well, we're going to cheat a little bit and use the Lewis model to give us a clue as to what the hybridization is. So we're going to draw a Lewis structure, and we're going to determine from the Lewis structure, we're going to determine the electron geometry. And that electron geometry is going to tell us the hybridization. All right. If the electron geometry is linear, it's going to be sp hybridization. Trigonal planar is going to be sp2, tetrahedral sp3, trigonal bipyramidal sp3d, and octahedral is going to be sp3d2. So let's see if we can predict the hybridization on each of these atoms. So here we have 1, 2, 3, 4 interior atoms. Let's see if we can predict the hybridization on each of these. So let's start with this one. How many electron groups? 1, 2, 3, 4. What's the electron geometry? Tetrahedral. So we go here and we see number of electron groups 4, tetrahedral. Aha, we know that's going to be sp3. Okay. This boron, how many electron groups? 1, 2, 3. What's the electron geometry? Trigonal planar. So we go back and we go, aha, 3 electron groups, trigonal planar. That's going to be sp2. All right. We go to this oxygen here, same as that one, 4 electron groups. So that's going to be sp3. This oxygen, 4 electron groups, it's going to be sp3 as well. All right, let's have you try one. First, write the Lewis structure for xenon difluoride and then determine the hybridization on the xenon. Go ahead and try that. Okay, the correct answer is D, sp3d. Why is that? Because when we draw the Lewis structure for xenon difluoride, it looks like this. Right? And if we look at the xenon, we have 1, 2, 3, 4, 5 electron groups, right? 5 electron groups. So we go back to our table, 5 electron groups. The electron geometry is trigonal bipyramidal, and the hybridization is sp3d. All right, so it's sp3d. All right, let's write a hybridization and bonding screen for this molecule. How do we do that? So we have Br, F3. Here's the Lewis structure. When you do a hybridization and bonding scheme, always start with the Lewis structure because the Lewis structure is going to guide you. Okay. We're then going to say, okay, here's a central atom. How many bonding groups? 1, 2, 3, 4, 5. So we know that the hybridization on the bromine is going to be sp3d. The fluorine is a terminal atom, right? So what kind of orbitals are involved there? Well, we got to look at the electron configuration for fluorine, and we know it's 2s2, 2p5, right? So what kind of orbital is going to be involved in bonding with the fluorine? It's going to be a p orbital, right? So then what we could do is we could go ahead and draw the central atom with the sp3d hybrid orbitals, so that we know that there's 5 lobes, 1, 2, 1 going into the paper, 1 coming out of the paper, and another one in the plane of the paper, right? And we can see from the Lewis structure that 2 of these are going to contain lone pairs. So these are going to be lone pairs. They're not going to be involved in bonding. The other 3 are going to form bonds, so we know that each of them is going to have 1 electron. And then they're going to bond with the fluorine atoms via p orbitals. Right, so we have bond there, and a bond there. So the last thing we have to do is just label the orbitals, label the bonds. And there's just 3 bonds here and they're all identical. So we just have to label 1. That's going to be sigma bromine, what kind of hybridization? sp3d, overlapping with fluorine, P, right? And there's our valence bond theory treatment of BRF3, okay? Looks like that. Isn't that a little nicer picture? Hopefully you get the idea. Here's just the labeling, right? Showing sp3d overlapping with fluorine P. Okay, let's do one last example. ONCl. So here we have the Lewis structure, right? So I'm not going to redraw it. We can just go and see, aha, okay, the oxygen atoms, the chlorine atoms are going to be unhybridized, right? Because they're terminal atoms. We'll start with a central atom. How many electron groups? 1, 2, 3, right? So we know that that's going to be on the nitrogen. We know that that hybridization is going to be sp2. Remember that sp2 hybridization always has a leftover p orbital. So I'm going to draw it like this. Here's one of my 3 sp2 hybrid orbitals. Here's another one, and here's another one. This one is going to be going into the page. This one's going to be coming out of the page. Okay. So I know that I'm going to form some bonds with those. Those are going to each have an electron. And then I have my unhybridized p orbital coming up and down, and that also has an electron. Okay, so if I again look at my Lewis structure, I know that I have 1, 2, 3 bonding, 3 electron groups. One of them is a lone pair. I'm going to go ahead and put my lone pair right here, right? And then I'm going to form a bond with the chlorine. On the chlorine, I know that the electron configuration is going to be, sorry, P1, 2, 3, 4, 5. So I know it's going to be through a p orbital. So I'm going to put the bond with the chlorine right here. And if I label that, right, it's going to be sigma nitrogen through its sp2 overlapping with chlorine P. Okay. Then I have to figure out this bond with the oxygen. So oxygen has sp like that, right? So I can form 2 bonds with p orbitals. So I'm going to write my oxygen here, 1 p orbital, 2 p orbitals. Each of them have filled. So here's one of my bonds. That's going to be called the sigma bond because it's end to end. Nitrogen, sp2 overlapping with oxygen p. And then I can form my pi bond here and here. And that's going to be nitrogen, pi nitrogen p overlapping with oxygen p. And there's my valence bond treatment of this molecule. All right. All right. Let's have you do this one. Go ahead and pause the video and see if you can answer this question. Okay, so the right answer here was D. All right, how do you know? Well, first thing you got to do is you draw the Lewis structure, right? SF4. Looks like that. Number of electrons is 6 for the sulfur plus 4 times 7 for the fluorines. That is going to be 34, right? So you go 1, 2, 3, 4, 5, 6, 7, 8, and you add in all these lone pair electrons on the fluorines. And so far we've used 32 electrons, so we got 2 more left. So we got to put them right here on the sulfur, expand the octet on the sulfur. Right? So now we go, okay, how many electron groups on the sulfur? 1, 2, 3, 4, 5. So what kind of hybridization is present on the sulfur? Well, for 5 electron groups, we know that's sp3d. So these bonds are going to be sulfur sigma sulfur sp3d, right? And what are they going to be overlapping with? On the fluorines, we know that we have s, p, 7 valence electrons. So we have one left over, one unpaired electron there. So that's going to be fluorine p, right? So it's the sp3d2 hybrid of sulfur and the 2p of fluorine. Okay, well, thank you for your attention on this lengthy video. Again, best holiday wishes to all of you, and I look forward to seeing you all in class on Monday. Bye.